this particle, of this cluster remains the same. That means that we keep the magnetization of the assembly even after treatment when they are in water. And so if you disperse the particle in water, you can, and you apply a magnetic field, you can see that the magnetic field, the particle self-assemble. And if you change the orientation of the magnetic field, you change the orientation of the dots. And you can see here that if you put a magnet progressively, you have all the particles going at the surface. And this system is stable, magnetically stable for several weeks. Instead of doing cobalt, we can do gold particles. And for you, as a optical well-known people, you know what's mean gold. So we use exactly the same procedure. We use the same procedure with gold. Just to mention here, you can see here, you have at the interface, you see a layer. That's probably cobalt oxide. Now with gold, you can see that you have the same behavior as before, except with gold, the diffraction is a little different. But as you can see here, the layer, the multi-layer of the DPPC attached to the gold surface. So then we have these clusters scattering in water, and we can do the absorption spectra. And if you do the absorption spectra of these large clusters, you can see that here we have a shoulder, and then we have a shoulder, and you have a shift toward large wavelengths when you increase the size of the clusters. So we decided to, I'm sorry, I hope you see the upper play, the top of the slide. I cannot see it, but I hope you see it. So to try to understand what was this shoulder, we changed the size of the supracrystals, and we found out that you can see progressively the shift on increasing the size of the system. So we try to determine the effective dielectric constant by using Maxwell-Garnett effective media. And this was done in collaboration with Pelouard. And then, so they simulate these different absorption spectra. And you can see here that progressively we have a double bond. And when you do all the experiments, you can see that, in fact, we have one peak which is constant, which is a localized surface placement resonance, as we all know for noble metal and for gold. And progressively here you have an increase of the shift of the peak, which is due to the collective mode. We start to have a meta material. So we have one thing, the fingerprint of the nanoparticle remain visible, remain existing in the optical property, and you will see later that is the same for other systems. And we have this collective mode. In collaboration with Giulio Cerullo and Della Valletta, Giuseppe Della Valletta, we use pump probe measurements on this system. And in fact, if you look at the pump, so you excite with the pump and you observe with the probe at different wavelengths. And you can see here that you have a short time, you have a well-known behavior which is due to electron phonon process. But then when you increase the time scale, you can see that we have a shift on the signal toward large wavelengths, and we have a signal at larger after 100 delay time, picosecond delay time. And that was not expected. So the electron phonon scattered in the noble metal, we found it as, so that's again a fingerprint of the single particle in the supracrystals, as we can see when we saw just a few minutes ago. So we really keep the fingerprints, but we also at longer time, you can see that that's the electron phonon which disappeared, but we see here an increase in the transmission. So Giulio, Cerullo, and De La Valette design a model from which they assume there are square lattices with the DPPC, with the alkyl chain of each nanoparticles surrounding by DPPC and water. And they found out that when they use at 400 nanometer, when it is at the plasma resonance, in fact, we have a very high penetration of light, and which is larger than what we observe in bulk. So we have the pump, which excites the metal, and then you have the pump absorption which initiate a chain of energy transfer having various energy degrees of freedom. So they use a model which is a temperature semi-classical model, and in this model they take into account the non-equilibrium electron in the metal, the thermal electron, the temperature effect, and the metal lattices. This gives a relaxation dynamic of the nanoparticles, and when they also couple this of the relative this temperature model with the organic system, and then they can determine the permittivity and compute. By doing this, they observe a very good agreement between the experimental and the semi-classical model at short delay time, a longer one, and you can see this signal, except here we will discuss this later, but the signal is stable even at more than 800 picoseconds. So that's support the model they developed, from which the light penetrates much more in supracrystals compared to the same diameter of spheres, and we have a degree of freedom inside the in fact, we create this give us we create a nanoreactor. In fact, so we have now a exceptional photothermal property, and you will see later that this is universal. But just now, you can see if you do the same experiments in dry medium, you don't have anything. You just have the electron phonon decay. So this is due to the presence of water. We don't know why, but this is due to the presence of water in the environment. And that's a good news. So here you see, you remember I just showed you that. And that's the signature, the fingerprint of mechanical property. And with other work we did with Giulio Cerullo and Dario Poli, we determined for cobalt in dry system, we determined the speed of sound inside the supracrystals. And then if you take into account this piece of sound, we can calculate the period, which is comparable to that what we observe here. So that's a good news. And it's furthermore, it's many years ago, 15 years ago, we did some, in collaboration with René Duval, we did some Raman experiments, and we found out that the Raman's peak is short, the bandwidth is shorter than for disorder assembly, for order assembly than disorder. And we explain this as a coherent vibration of the nanoparticle in the supracrystals. That's totally coherent with what we observed a century ago. So now, instead of using clusters, we will try to use colloid ozone and supraball. And then we will see the nanomechanical property, and we will use this system for internalizing tumor cell. And so the colloid ozone, we create that as instabilities. And in fact, is if you can see here, you have the particle forming a shell, and inside is hollow. And more, you have a particle which are one layer, but many of the colloid ozone are several layers. You can see here is only one layer, but here you have several, 2-3 layers. And this in collaboration with Per Larsen, we just signed a paper on that recently. You can see that from the tomography, you can see that we have steps. That's just a layer. In this case, it was one colloid ozone with 2 layers. And the system is, I will come back to that later, but the system is highly flexible, and you will see it's very important for biomedicine. Then we have also supraball, and the supraball you can see here. You can see here that you have steps, and this is well known. Many groups work on this, but on very large scale. And again, if you look at the tomography, you can see that you have steps. And so if you look at these 2 types of colloid ozone, just a shell, or a supraball is an FCC, the nanoparticles are self-assembled in FCC structures, and with some steps at the edge. But you can see the diffraction is the real crystals. So when you compare the colloid ozone and the supraball, we look at the topography, the adhesion, and you can see that the deformation, you can see that the colloid ozone has a very strong adhesion just at the edge, where when the colloid ozone doesn't have it. And so similarly, they deform, highly deform. The colloid ozone is able to deform, which is not the case of supraball, because supraball is FCC supracrystals. And as you can see here, the Young modulus of colloid ozone is very small compared to the supraball. And the stiffness of colloid ozone are very low compared to supraball. So we will have 2 systems made by the same particle, this ferrite particle, Fe3O4, one forming a shell and very flexible and with a large adhesion, and the other one, which is FCC, more solid. Even the Young modulus is not very large, and it's around 100, 200 megapascal, but is very large compared to the colloid ozone. And we will use this for internalization in cells. So we will compare the internalization of isolated particles, the same ferrite. The particles now are dispersed in water, either dispersed in water or colloidosome or supraball. And here we make the assumption that the fact that we have hydrophobic in colloidosome and in supraball, we are hydrophobic system. Again, the ferrite here, the ferrite, this one, the ferrite forming the shell are hydrophobic. And we just add a surfactant to make them hydrophilic, but the particles are hydrophobic. And here also, the particles are hydrophobic, and we just add some DDAB to let them solubilize in water, disperse in water. And now we will use this. Here we have the water-soluble particles, and here you have hydrophobic, same particle, hydrophobic particle, but dispersed in water. And here the same. And here the difference is the flexibility, the deformation. And we will wait, we will make into contact this part, either these three, with a cancer cell. And we will look what's happened when you change the system. So when you have a nanoparticle dispersed in water, you can see that some of the particles are internalized in the cells, and you can see they are forming small clusters. Now, so the particles are just internalized, and this many people, a lot of people has been working on this. Huh? But now look at the colloidosome. The colloidosome, looks at the size, is around 300-400 nanometers. After internalization, you keep the self-assembly, but now we are more or less a factor of 10 compared to the dispersed particle in water. That means that, and you can see that the particles self-assemble, and the self-assemble seems to self-assemble in specific region, and we keep more or less the shape, but what is important, we keep the self-assembly. And for the supraball, we also keep the self-assembly. That means that if you internalize this system, you have, for the colloidosome, you have a huge increase in the size, but you still have the self-assembly. And for supraball, you keep more or less the size. It's a little larger because you have some exchange, but we keep the size, and it remains self-assembled. I would not say here it's FCC. I don't know if it is FCC here. I am not sure. But in any case, it's self-assembled. So they both conserve the self-assembly. And so you can see that ferrite is, you keep the assembly. And that was the challenge and the concept we wanted to develop, to try to keep the assembly of the nanoparticle inside the cell. If you wait for more, 8 days, you can see that the particles, dispersed particles, are just start to disintegrate, but here, for the colloidosome and the supraball, they remain as they are. And if you do small angle X-ray scattering, what we did small angle X-ray scattering, and we extract the diffusion due to the cell. So what you see here is just a diffusion of the particles. And if you look at the structure factor, you can see for the nanoparticle dispersed in the cell, you have a slope here of the structure factor, which is 1.7, which is just a cluster, formation of clusters, of disordered clusters. At the opposite, when you have colloid ozone and when you have supraball, you increase considerably the slope of the structure, the form factor, the structure factor, and that's a signature that the particle remain highly packed. So we have the signature not only by TM but by Sachs, where it's more average for the system. We keep the assembly of the system we keep the packing of the nanoparticle inside the cells. And if you look at here, that we don't have exactly the explanation, but here you can see a shoulder which does not exist here. And this shoulder could be due to the interaction between some clusters, small clusters inside the cells. But we don't have any, it's specific, highly reproductive, but we don't know really what is it. So now the question, if you look at this photo, this TM, it seems to be that in a lysosome, you have more or less a distribution, average distribution of the particle for the dispersed, but here it seems to be we have a specific distribution. And furthermore, it looks like we have more nanoparticles by using colloid ozone or supraball than for dispersed particles. So we try to make more quantitative data, and we just use some lysosome and look at the dispersion of the particles. And we did that after 1 day incubation and 8 day incubation. And you can see that after 1 day incubation, you have a factor of 8.5 more ferrite particle by using colloid ozone, 13 by using supraball, compared to the dispersed particles. Yeah, you have the number here. And after 8 days, the amount is a little less, but we still have almost 3 times more ferrite particles inside the cells compared to using dispersed nanoparticles. That was published last August in Ozone Functional Material. Now we will try, if you look at the picture here, it looks like that you have a specific orientation of the system. So we assume that we look what's happened in the distance of 100 nanometer from the membrane, lysosomal membrane. And when you do that, when you make the calculation, just by looking at the contrast, you can see that after 1 day incubation, you have a factor of 10 more particles, colloid particles at close to the membrane than if you use dispersed particles. And you have less with 8 days, but you still have quite a factor of 5. This factor is less important with supraball. And after 8 days, you can see that we still have much more nanoparticle close to the surface, to the membrane. Then, however, you can see that we have a drop. It seems that with supraball, the supraball are expelled from the membrane. But this is very important because you know that one of the problems in bio something
is to break the membrane, because usually this membrane is very solid. It does not is not easy to break it. So to put a lot of material, nanoparticle, close to the membrane, it seems to be a good idea, good news. So now let's look at the magnetic property. If you apply a magnetic field, you cannot see anything with dispersed particles, but you can see with colloid ozone and supraball, you can see the field, you can see the particle self-assemble, and you can see also that you have the orientation inside the formation of chain in inter and intracellular phase. So that means that you really, the particle, you can manage to have this particle oriented. And you can see in the next slide, for colloid ozone, if you apply a magnetic field and if you change, so you are oriented the assembly in one direction, and if you change the orientation, you can see you have a change of the orientation. But some of the assembly does not change with the same velocity. With the supraball is more difficult. With supraball, you can see here when the applied field is the applied magnetic field is in one direction. If you change, it takes some time to get a change. It seems to be more rigid. But anyway, now we have a system in which you can monitor, you can move, let's say, particle moving inside the cells. And so now we will end with the eggs. So the eggs, we will use the same instabilities, and instead of colloid ozone, we will try to fill with supracrystals. And here you can see is ferrite particles again, and you can see they are filled with supracrystals of ferrite nanoparticles also. And these supracrystals is FCC supracrystals. And you can also use two types of material, ferrite and gold, and then you create another type of eggs, which is a binary system. And you can see it's a cube. You can really see the shape of the supracrystal is a cube. And if you look carefully, you can see you have really gold and ferrite really well ordered, and you can see from the chemical maps they are really well ordered. So now we have and just for both of you, for Cecilia and Raoul, you can see also now we have the ferrite and gold inside, and we change the size of the gold supracrystals, and you can see here that's a chemical analysis of this system, and you can see that progressively you fill the shell with the gold, and you can see that the gold is FCC. The system is self-assembling in FCC. So we did not do anything yet on this one, but I would like to come back to the nanometer I showed you before. And as I told you already, I already tell you that we have the fingerprints, but if you look at the different systems, the supraball, you can find the electron phonon, and for the X also. So you have more or less, of course, it depends on the material. Here you have ferrite, here you have ferrite gold, and a shell of ferrite, so it's more difficult to identify what is what,
but you can still have the fingerprint, the electron phonon behavior. And if you look at the long time, which is our nano ether, you can see that in all the case, we have this long time behavior. That means that whatever we use, if we have supracrystals in water, you can create a nanoreactor, a nano ether. And that will not be, I think, I did not check anything, but I think it will not only can be used for biomedicine, it can be used for solar energy. I did not try yet, but that could be one of the purpose of this study. I think these systems are very rich and could really be developed in different areas. In our case, we look at the hyperthermia, and as I told you, this paper has been just accepted today. And here we incubate the particles, either the particles or the colloidosome or the here is the supra ball, and we have the control, and then we irradiate the system, and then we let incubate for 4 hours. And after, if you don't have an irradiation, you keep more or less the same. The system does not change, but when you irradiate it, you can see here the pink and the yellow are correspond to death particle, either by necrosis or by apoptosis, but they are dead. Now, if you, instead of that, if you do the same experiments with, but by having a monolayer of cells, and irradiate the monolayers, you have a huge amount of cells which died, compared to the dispersed particle. And here is the effect is much larger here. That's really indicate that we have local heater. The nano heater behave locally. And what we did is we use a Ville tendon, and we deposit the colloidosome. Again, you can see the colloidosome is much larger here than in solution, and is deformed. And then we irradiated the system, and you can see you have a superb hole. The particle the tendon is broken. And with the super ball, you can see the same. But we have other examples where the colloidosome seems to be much more efficient to kill whatever they have after getting irradiated. So in conclusion, I hope I convince you that we have developed some new concept, and the cluster system, which is supracrystals coated with biomolecule, we keep their integrity for a long time. With cobalt, we form a CO layer which protects against oxidation, the clusters, and the magnetic properties are maintained, and we can manipulate it also. With gold, we have 2 absorption peaks, one due to collective mode, which evolve linearly with the size, and we got the fingerprints of the localized sulfur-plasmon resonance. Concerning the colloidosome, we develop a new concept for controlling the intracellular distribution, the order, the fat, and the manipulation of ferrite nanoparticles in the organelle. And so the supracrystal remains self-assembled. You have a long distance cluster interaction inside the cells. You improve the uptake compared to the building block. Do you remember? It's almost a factor of 5, but can be reached 10, 12, 13. Mainly, the particles, the nanocrystals are localized at the liposome membrane. We increase the factor of 10, and you have magnetic manipulation. And we have a high terminal, I don't know if it is really English, property. So for all, we get the fingerprints of the part of the building block, and the nanometer, from the data obtained by Giulio Cerullo and Giuseppe della Valle, you can see that we create a type of nanometer, and you cannot get this if you don't have water. You need to have water to get the nanometer. And we get the fingerprints of the mechanical property we already observed 15 years ago in dry system. So I need to thank very much these people, because nothing will be done without them. And thank you very much for your attention. Voilà.
Thank you, Marie-Paul. So questions, you can send me the questions through chat, or for those of you watching YouTube, you can write it on the chat of YouTube. And Maria Esther Brandan has a question. Maria Esther?
Sorry. There. Can you hear me?
Yes.
Yes. Thank you much. Well, congratulations for this excellent presentation. Concerning your work introducing these particles into the lysosomes, how far is their knowledge or the technique from being able to attempt disrupting the reproduction, I mean, the multiplication of cancer cells? Or what is, I imagine is that your final goal or not? So maybe it's a composite question. If it is, how far are you? Or if not, what is the final biological or biomedical goal?
Oh, I think I don't have all the answer on that, but let's say for sure, it seems to be that hyperthermia could be a very important role, but we have right now. I'm not sure. Voilà, I'm still open to look at different type of application. For sure, hyperthermia work. We found that and we found that the colloid ozone goes to specific system compared to the others, but we did not go far away enough to know exactly what is the behavior. It's just at the starting point.
Okay, thank you very much.
Other questions? Marie-Paul, while they ask, I have a question, Marie-Paul. Where you discussed the mechanical vibrations of the supracrystals,
yeah,
you reported a speed of sound of around 1200 meters per second.
Yeah.
Now, that's the supracrystal is made also of gold nanoparticles?
No, the speed of sound we measure. In fact, what we did, it was we use a substrate and deposit thin supracrystals, cobalt supracrystals, and we found out some propagative phonon. And from this, when we did this at different angle, incident angle, and from that we deduced the if I remember well, the speed of sound. And the speed of sound depends on the est-ce que c'est vrai ça? I forget now. I have to check. But the speed of sound at room temperature was this value. We took this value from what we did with Giulio and Dario, Giulio Cerullo and Dario Poli with cobalt particles. But we assumed that it was the same.
But these were in water, right?
No, that was in dry system.
Ah, dry system. Okay, thank you.
It was in dry system. I can send you the paper if you want.
Ah, yes, please, thank you.
Yeah.
So, let's see, more questions. Let's see. Let's see, Gerardo Garcia, you have a question? No, I think questions.
Giuseppe seems to have raised his hand.
Giuseppe. Gracias. Giuseppe.
Yeah. Hello.
Sí te escuchamos.
I don't listen.
Se está cortando, Giuseppe.
We have problem.
Okay. So can you quantify how much do the particles?
How much?
Let's say, can you quantify how much the?
There is some discrepancy. I cannot get your question.
Giuseppe, si
Can
quieres
I
escribir tu pregunta en el chat.
quantify what? What can I quantify?
Let's see if he can connect or if he can write his questions. If he can send me his questions through the chat.
Okay.
Más preguntas. Let's see from the YouTube. Si tienen preguntas. Cecilia and Cecilia.
Yes, thank you. I have a question. With the information that you have, you can estimate how much of the energy transform in heat in the surroundings, or is not possible with this kind of excitations and the measurements that?
I contact one guy, but who is a Chinese guy who can't quantify, but usually he can do it in dry system.
Okay.
And, but we did not quantify it. But I try to quantify it because that would be nice. But I wrote to him, and he apparently I wrote to him 2 weeks ago, and he said I will try to read your paper, but from what I see, he can. All the experiments he did was in dry system, so I don't know if he can do in water.
Okay.
It has not been done.
Okay. Thank you.
Giuseppe, do you want to try again? If not, I read your question.
Giuseppe.
Let's see. He's wait. That he asked. That how much the particle moves in nanometers in when you excite the phonon in the clusters, like how much the particles move in nanometers. That I guess that's the question of Giuseppe.
Could you repeat?
I lost it. Wait.
When I
you excite phonons in the cluster,
yeah.
How much the particles move in nanometers?
I know the particles stay, I think the particles stay together, stay fixed, and just the bracing is collective.
Okay.
The particles stay at the same position, but you have a current bracing inside the supracrystals.
Okay, so let's see if Giuseppe answers something. In the meanwhile, he just reports that has bad connection. Okay, Gerardo Garcia Naumis. Can you explain what kind of theoretical simulation was made to reproduce the oscillations at 300 picoseconds, that is?
Here?
Yes, please.
That's?
Okay. Yeah, exactly, that one. Yeah.
So here we measure the oscillation, okay? And it's around 300 picoseconds.
And his question was what kind of theoretical simulation was done?
Because
was just from the experiments. Here we have done, Duval did some simulation. He took exactly the same, so Duval, before this type of experiments, he did some experiments to show the bracing mode of atom inside the nanoparticles. And he used the same model, and from the for nanoparticles in the supracrystals. But I don't have the detail here. Sorry, but you can have a look on this paper on 2005. It's too long for me now.
okay, thank you very much.
But you can go to
Yeah.
share material, this paper, and I can send to Raoul also the model. Yeah,
Model, yeah, exactly.
Wrote a model on that. He did a model, and I will send you. I will send Raoul the model, and then he will send you back. Okay.
Okay. Thank you very much. Yeah.
You are welcome.
There's a follow-up on Giuseppe's question. I think he says that if the supracrystal is in a breathing mode, the individual particles that make the supracrystal vibrate.
Yes.
So a breathing mode. So his question is each individual particle, how much it vibrates. If you can quantify the vibration of the individual components of the supracrystal.
I don't understand what you said.
I guess
my system is broken now. Okay, let's go. We will try to. Here you can see we have the. I did not catch your question.
I think that the question of Giuseppe also was like if you can quantify the vibrations of the individual components of the supracrystal.
Oh no. You know, it was based by the fact that just the bandwidth of the quadruple mode was smaller for particles self-assembled than disordered. But we did not quantify. No, there is no quantification.
Luis Alberto Medina has a question. Luis Alberto, por favor.
Yes, thank you. I just have a concern about, it looks really nice, the experiment in vitro, in cells, but how are you planning to try this or to evaluate this in vivo? Because in a model, in a cancer model with a xenograph, the principal concern that I see is how will you be able to transport these kind of particles directly into the tumor? And also, I have a question. Did you measure the zeta potential to try to see if the systems aggregates in just because the characteristics of the charge of the particles or the structure of the particles?
The structure, we did not do this, but from what we we inject in the mice, and we took a slide. So first, the mice are very well healthy with these particles. That's good. And the second one is we inject on cancer tumor or tumor, and then we make a slide, and we found the particle self-assembled again. But that's it. We did not do something else.
It was an intratumoral injection, right?
Yeah.
Okay, but that is not a common in a real situation. You will need to inject that by intravenous injection.
Yeah.
So that will be the problem. How you will control the movement of these particles in the bloodstream, and how you will guarantee?
Well, right now, it was when we started this, nobody was. We were not sure that to succeed is the first step. The road is long now. We are a long road to go to more quantified and to have a better understanding. But right now, it's just a first step.
Okay, thank you.
Any more questions? So it's not just an announcement. Next year in the Cancun meeting of material science, Maripol is going to be one of the plenary speakers.
Thank you very much. We will have a good time.
And so you are invited to go to the conference in Cancun. If there are not any more questions, I think we can only thank Maripol. I don't have the automatic applause thing here, but congratulations,
okay.
and thank you for your talk.
It was nice to see you.
Okay.
So be safe, and thank you very much to give me the opportunity to show you our last data.
Thank you.
Thank you very much.
Bye-bye.
Thank you.
Interesting conference, Maripol.
Thank you so much. Bye-bye.
Thank you, Maripol. Thank you for
Take care.
talk.
Bye-bye.
Merci
Take
beaucoup,
care.
Marie-Paul.
Merci. Merci à vous.
Merci.
Au revoir.
Au
Bye-bye.
revoir.
Bye-bye.
Au revoir.
Bye.
Bye-bye.
De la